design and drawing of foundation retaining wall. Students, in the previous sessions, we have stopped here. In that session, we have gone through how we are going to calculate the depth of the foundation, and after that, how we are going to check for the one-way shear. If the depth is not sufficient, how we are going to revise the depth of the foundation using what formula, then how we are going to calculate the longitudinal reinforcement using the moment what we got from the bending moment diagram. Now, after calculating the, if you look at here, so I already told you the moment what we are going to use here is to calculate the reinforcement for sagging moment. We are going to use sagging moment here. That for hogging moment, that is at midspan, we are going to use hogging moment here. So that is what I have written here. In case if you forget my wordings in the video, so you can see here. For hogging reinforcement, mu is the hogging moment, and for sagging reinforcement, mu is the sagging moment. So this way you are going to calculate the reinforcement at different portions of the foundation. We know we are not going to use one particular moment for entire foundation, because in the sagging moment is not that greater than the hogging moment. So if you use the higher moment value, the AST provided the sagging portion will not be it is not be economical thing. So if the sagging moment is much more lesser than the hogging moment, so that we are going to use that moment only for the sagging reinforcement. So keep that point in the mind. Now we look at the checks, what we are going to, how we are going to check for one-way shear. So I already told you the critical part, the critical portion of one-way shear is at a distance d from the face of the column. This d is the depth of the foundation. So here also the checking for one-way shear will be done for the heavy column only. So I already told you, if it is if it is safe in case of heavy column, definitely it will be safe for light column also. Here, there we calculate the shear force by using upward pressure on the perimeter area. Here the area is different. It is not perimeter thing. So it is only in one direction. So here there is one more formula we are going to use to know the shear force. In the shear force diagram, you know the shear force at particular point, just right and just left. Let me go back to that slide. I will show the thing. So here you see this one. In this case, I consider that this is the heavy column. That is, B column is the heavy column. So this is the value which is the shear force just left of this point, and this is the shear force value which is just right of this point. So why I consider the shear force just right of this point for this column is the critical section for one-way shear is at the in this side of the column, the right side of the column only. It is not left side of the column. If the heavy column is this one, for suppose A is the heavy column, then we need to consider shear force just left of that point, that is this value. This is the shear force just right of this right of that point. So because the one-way shear critical section will be left side of this point, so I consider this column as a heavy column. So I am considering shear force just right of this point, that is the W8. This is the shear force just right of that column. So that is the basic funda behind it. If in case in the examination, if the heavy column is this one, we have to consider shear just left of this column, not the right of it, because the critical section will be left side of this point. So that way we are going to calculate the shear force. Then we are going to factor that shear force by multiplying with 1.5. Next, we are going to calculate the shear stress by using this formula, VU by BD. So then uh, by we already design AST for the column. So what is now here, we are going to check the reinforcement at this portion. So here this portion AST is different, this portion AST is different. So we have to consider this AST only, the sagging reinforcement only. So by considering that AST, so you have a table 19 in IS 456. So you decide the grade of the concrete by using the grade of concrete and the percentage of the steel you are provided the sagging portion. So you can take the tau c value from the table 19. So from tau c value, we are going to calculate the tau v bar using this formula. So I already mentioned about Ks, where we are going to take the Ks value also. If this the nominal shear stress whatever we calculated earlier, if it is less than tau v bar, then we are going to provide the nominal shear reinforcement using this formula. So to find the spacing of this one, or else we are going to design for the shear. We are going to design shear reinforcement using this formula. By this way, we are going to check one-way shear. After the foundation is passing in one-way shear, then the final step in the design of combined footing is to calculate the transverse reinforcement. That is the final step. So this is the bending profile in transverse direction. So we used to find the reinforcement in longitudinal direction, we use the bending profile in this direction. Now we are going to use this profile for calculating the transverse reinforcement. If you look at this carefully, here it is act as a support, and this portion will be act as a cantilever beam. So here it is going. Now we are going to design as a cantilever beam only. So you already studied structural analysis. So at which point the bending moment will be more in cantilever beam? Anyone? So at the support of the cantilever beam will be experiencing the maximum bending moment, because it's a free end. So total moment will be transferred to the support. So now for the transverse reinforcement, definitely the critical portion is at the support. So the point is, in longitudinal reinforcement calculation, we have seen the bending profile will all over the length, but in transverse direction the bending won't be all over the length. It will be near the combined footing will bend in transverse direction at the near to the column only. So at what distance it is going to bend, we have to find. So as per the code, the combined footing will bend near to the column at a distance from the column is d from either side of the column. So if you take the breadth of the column is b, the portion which is going to bend in transverse direction is b dash, that is b plus 2d. So d in this direction, d in this direction. After this point, the combined footing won't experience the transverse bending. It will bend only in longitudinal direction. So we no need to calculate the transverse reinforcement for this portion. So we are going to calculate the transverse reinforcement for this portion only, and we are going to provide the transverse reinforcement for this portion only. That's why the area which is subject to transverse bending will be calculated as b into b dash. So after that, I already told you b dash is the width of the column plus 2 into d. So the net upward pressure will be W1 into B1 into B dash if we are calculating the transverse reinforcement at A column. If we are calculating the transverse reinforcement at B column, we have to use W2 here. So after calculating the net upward pressure, then we are going to calculate the bending moment using this value. So I already told you this will act as a cantilever. In the cantilever, bending moment formula will be WA square by 2, because it is the UDL. WA is the load and distance is from the half of the distance we are going to multiply with the load in the bending moment calculation of cantilever beam. Then we are going to factor that moment, and we use this moment in calculating the AST and transverse reinforcement in the same formula. Here the B we are going to use is 100 meters. So here the AST is area of reinforcement per meter. First we are going to calculate the AST per meter. Then we can translate into whatever the length we want, because we are not going to place the transverse reinforcement all over the foundation. So we are going to use the transverse reinforcement for particular length only. So to make the calculations easier, first we calculate the AST for per meter. Then if the AST per meter is 1000 mm square, if what is the area AST for 1.5 meter, will just simply multiply 1000 with 1.5 meter, right? So first we calculate the AST per meter, then we will see the spacing of the reinforcement. So that is how we are going to design the transverse reinforcement. With this we are going to end the design of total combined footings. Then we are going to use these values, this longitudinal reinforcement and the area of the foundation, spacing between the longitudinal reinforcement and spacing between the transverse reinforcement, to detail the foundation. That also we have to do. So that detailing and the calculations we are going to discuss in next lecture. So by then we are going to get clear cut idea about how we are going to design for the combined footing. Then I will be giving one more assignment on design of the combined footing. Thank you. We'll see you in the next session.